Reinforcement learning is one of the flakiest things I know. It is very hard to get it right. Maybe I was simply not good enough to get it right, but man, it's hard. You require a lot of tricks to make it perform well. And you will see the same case with reinforcement learning from human feedback for large language models. It does not work out of the box. You have to do a couple of tricks.
Using a reinforcement algorithm, but they were trying to maximize impressions on users. So they wanted users to see as many adverts as possible. But whereas what they should have done is optimize for hang time, where people would be eyeballs staring at products. Because what maximizing impression means is that they will feed you crap, so you scroll to the next advert as fast.
Nice.
So this is a really good example of taking the wrong reward.
They did not fix it, so that's for sure. Twitter ads are garbage.
Because we make these choices every day, right? How do we, especially during COVID pandemic, who do we prioritize to, put on the ventilator? How do we balance these risks? And how do we imbue language models with the ethics and Hippocratic oath that doctors take?
Hello and welcome to another episode of the Dev and Doc podcast. Today we'll be talking about reinforcement learning from human feedback. This will be, I think, more of a tutorial and really going into the details of how is reinforcement learning from human feedback done, and a bit of a course if you want.
No, this is the exciting one because we've been meaning to do this for a while. And I know a bit about it, but I'm looking forward to learning more as a doctor.
Perfect. I mean, I was thinking we are a bit late because reinforcement learning people are using from human feedback for LLMs. People are doing these for now a bit over a year and a half. We have records that where people have used this in 2018 and even before that, but the most popular part was with ChatGPT, so that's a year and a half.
I mean, we're late in terms of the hype, but we're not late in terms of education.
Okay, I agree.
No, seriously, but working as a doctor, I really spend a lot of time thinking about how we can make language models more aligned with clinicians, right? Because, we're aligning it with human feedback, but we never talk about aligning to clinician feedback.
True. Yeah, that's true. We don't really, most of the, I assume that in all of the alignment that OpenAI has done, there might be some doctors in there, but...
Do you think so?
I think so.
What doctor's going to have time to annotate for OpenAI?
I don't know. They'll hire someone, give them a full-time job to just annotate. This has could be.
Initially we read those articles about OpenAI hiring basically mass factories of people from, that particular one was in Africa, but there's also other companies like Scale AI in the US that basically are AI companies designed to have loads of people to help drive that either annotation or reinforcement learning with human feedback. Basically giving human feedback to train models. That's an entire business.
No, that's true. Okay, we don't know. I'm just saying could be that some doctors are doing it, could be not. I'm just thinking because even still the model can answer some medical questions. So, and it provides some explanations that are part of, I don't know, to some extent follow some medical literature. So could be that a bit of
but that's the interesting thing, right? There's medical data in the internet and in the base model. What I don't think it answers in a way that's optimized for doctors.
It answers in a way that's optimized for general public, but not really.
Exactly.
Okay, that makes sense.
And one side point before we begin, on the concept of alignment. So we talk about making AI models aligned with what we want, right? One thing I'd never have seen any papers on is the ethics, the ethical direction of a model. Like there are studies on the political bias of models, right?
Yes.
So, I mean, I might be wrong, but I think ChatGPT is slightly more liberal because of the data that exists online. But you know, no one looks at the political compass or moral compass of a large language model.
There are papers. So there are papers where they have studied also the moral compass.
Really?
Where they also have seen that you can trick it so that the moral compass goes a bit in the wrong direction. There are papers for that. So there are papers. Oh man, I just read one a couple of days ago. We'll link it if I find it.
But are there ones where you approached very tricky scenarios, like deciding between patient X and patient Y with this condition?
Oh, not for patients. There was one for war. There was one where the model was put in a situation, should it go to war or should it not go to war? And then after, resolving a situation peacefully or not really peacefully. And what they just saw is that the model does have a bit of tendencies to resolve to arms over over really just resolving it peacefully.
But you know, so that's an example, and there's stripped down versions of that, right? There's I don't know, have you heard of the trolley problem, which is very popular online?
Yes. Yeah.
You know, so it's like, oh, a train is going in this direction, it's going to run over like 3 guys. Will you pull the lever to change the track to run over just one person? You know, stuff like this. And I've tried this with language models, but obviously they've put in all kinds of safeguards now. Yeah. So if I ask it anything like that, they'll be like, oh, we're not going to run over anyone. We can't answer this question. Blah, blah, blah.
No, but you have studies for that. There are quite a few of ethical studies, and especially because this goes into safety, and a lot of people have done papers on safety.
But not in medicine. That's my point. Like, or not that I've come across.
Yeah.
Because we make these choices every day, right? Like, you know, how do we, especially during COVID pandemic, who do we prioritize to, you know, put on the ventilator? Who, you know, how do we balance these risks? And how do we imbue language models with the ethics and Hippocratic oath that doctors take? I think it's a very interesting topic, and I would love to see more research on that.
No, for sure. I think one of that, a piece of that is also because hospital data are not accessible and all of that, and you cannot really put a real scenario into a model because you would need to run it on premise, and the current models that you can run on premise are not that good. So I think there are still many reasons why it's not being done. We go back to reinforcement learning from human feedback. We'll call this RLHF. Currently, that next to DPO, direct preference optimization, are the 2 most widely used approaches for alignment of large language models to human preference. But before we go into reinforcement learning, I would just want to cover a bit about machine learning itself so that we are sure what is reinforcement learning. We just know what's that before we go into RLHF. So
sounds good.
Okay, so as you know, like we have 3 types of machine learning, 3 big types. Supervised, unsupervised, and reinforcement. I think supervised is the easiest. It is also the one that is most widely used and that gives the best performance currently. We will come to self-supervised learning in a second, but just stick with these for a second. So supervised has a history of like 30-40 years, and it is really one of the most widely used. And what it just means is that you need to provide labels. You have your data set, you need to manually annotate that data set, assuming like I have my data set of 50 patients and I want to annotate which one of them is well, which one of them is not well. I would just have a doctor look at that, annotate those 50 examples, then I will train my model. That can be a transformer, an LSTM, whatever type of deep learning network, basically.
Yeah, it's like learn by seeing. So in the example of, you know, identifying, let's say, brain tumors in MRI scans, a doctor will actually, or a radiologist will sit there and demarcate each of the tumor, and then say to the model, look, this is where the tumor is, this is what we think,
Yes.
and then through iterations of that and through many examples, the model learns how to identify tumors and brain scans.
Yeah, exactly. So that's an example from machine vision.
Yeah.
It is the same in every other area. And then we have unsupervised learning, which the main benefit of this one is it does not need labels.
Mm-hmm.
So for example, if you go again with our 50 patients and assume every one of those patients has certain characteristics.
Mm-hmm.
So assume has some features, and those features can be like, what conditions does the patient have? What are the symptoms? For example, what's the body temperature? So we have like 10 of these features, and I would feed those 50 patients into a clustering algorithm, which is a type of a unsupervised algorithm. And I would tell it, okay, cluster now these 50 patients into 5 groups. It would try to find similarities between those patients, and in some way, whichever way it knows to do it best, it will give me 5 clusters or 5 groups of those patients.
So yeah, so in a way you're creating like a Venn diagram. So you're saying, here's the data, how do these sit and how do they overlap? Or how do they cluster separately?
Yeah, I mean, not a Venn diagram in a sense, because you are basically creating 5 different groups. So there is no overlap between the groups. You will just, because clustering will separate them into 5 groups, or however many groups you want. The only disadvantage of this is you cannot force the model to separate them into the groups that you need. So I might want to separate the patients into groups of, I don't know, who is sick or who is not sick, or in a scale of 1 meaning they are not sick at all, 5 meaning they are very sick. But the model can decide to classify them based on the type of the disease. So someone has cardiovascular problems, so the model might decide, okay, these patients have cardiovascular problems. These patients have whatever, other issues. So it might create 5 groups that are not the 5 groups that you want. So unsupervised clustering will simply find groups of patients, but you do not really have the way to steer them in the direction you want. So that is unsupervised. Then there is self-supervised. So we said there are 3 main ones: unsupervised, supervised, and reinforcement.
You said,
yeah, and self-supervised is a bit of a mix. This is currently the one that is used the most because LLMs are trained with self-supervised. And what this just means is that, to be honest, this is simply supervised learning because you are providing the labels to the model. People called it self-supervised because you are not explicitly labeling the data. So you don't go through the text and explicitly say what word comes next, and because you can use old historical data. So I can use like textbooks or any kind of text that is ever written, I can use that. But someone still had to make it. Someone still
so it's
had
like a
to...
lazy form of supervised. It's like you take what's already out there and
exactly.
you just kind of learn from it if possible.
Exactly that. So that's it. So basically it is a bit of, people still say like, oh, it's maybe a bit of unsupervised because I did not have to manually annotate the data, but still someone had to go in and write all of that data in the past. So it's a bit...
Okay.
Yeah.
I think I've got the perfect analogy. So
yeah.
Basically see it as parenting, right? So,
okay.
So unsupervised training is like the parents is not there. They're just leaving the kid to wander around and learn for themselves. And they're just like, whatever
happens.
I'm not involved.
Yeah.
I'm going to the shop and I'm not coming back. And then supervised is obviously the supervising, the teaching the child how to learn. They're going through, taking the time really, just pointing out how to do things and learning from there. And then self-supervised is kind of like the lazy parent, where maybe they just buy a couple of textbooks from the shop, and then they're like, just do the textbook.
Read the books.
I'm going to watch TV, but I'm here if you need me, kind of thing.
I agree. I think it's good. There will be, you will see, like once we now go into reinforcement learning, there is a bit of mixture there. But okay, let's go into reinforcement learning, so we'll see what's the part that's missing. So with reinforcement learning, I'll simplify this as much as possible. Reinforcement learning, I didn't spend too much time on it. I spent maybe 1 year doing pure reinforcement learning.
That's fair enough.
Playing around with building games and making bots that can play Minecraft.
Okay.
So it was not but I don't know, it became like very popular during the time of DeepMind when they put out AlphaGo and beat basically the world champion.
And they played all the Atari games.
Yes, all the Atari games. So I saw that, I was like, I want to play games also. So I was basically doing reinforcement learning during
So you did that?
Yeah.
So why didn't you do it for RuneScape? You can just farm loads of money and then sell characters.
Okay, I was not that into games. I was playing Minecraft a bit. Yeah. No, you'll see, reinforcement learning is one of the flakiest things I know. It is very hard to get it right. Maybe I was simply not good enough to get it right, but man, it's hard. You require a lot of tricks to make it perform well. And you will see the same case with reinforcement learning from human feedback for large language models. It does not work out of the box. You have to do a couple of tricks. Okay, but to go back to the simplest thing ever, do you know, how much do you know about reinforcement learning? What would you say is our reinforcement learning?
I'd say going back to that analogy of the parent.
Yeah.
You basically, it's like training a dog.
Okay.
or just using both positive and negative feedback to essentially condition and train either pets or
anything
your
else.
children.
Yeah.
So if they do something, in this case you don't provide any explicit instructions, but if they do something well, you give them a treat, right? Whether that's a snack or you buy them a present, whatever. Like if your child does well in a school exam, you reward them with something. Money. I mean, or just quality time maybe, or
True.
And then if they do something bad, so this is optional, but I know you can also kind of put negative reinforcement learning as well. So if they do something wrong, something bad, then you penalize them. You can take stuff away, you can ground them, etc., etc. So it's just doing that for models, and to do that you set kind of a reward function and a kind of punishment function. And so I think for some of the Atari games, for example, they set the reward as the score, or I don't know, if chess to checkmate or get the king or whatever.
Win or lose. Yes. No, but that's basically exactly right. In reinforcement learning, you have an agent, which can be like a machine learning model, a deep learning model, a large language model, whatever else you want. You have some kind of an environment. The agent usually knows a bit about rules and what it can do, what it cannot do. So if it's in chess, you give it the rules of chess. You don't allow it to do whatever it wants. You give it the rules of chess, and the model knows what it can do. And basically at every point in time, the agent makes an action. The environment changes based on that action. In chess, basically that would be a move on the chessboard. Then the opponent would also make a move. And then you would have a reward function that calculates now how good is the state of the current chessboard for the agent, so for the machine learning model. And based on that, the reward can be high or low. Now there are many complications here, because sometimes you cannot determine is the position good or bad. You cannot determine the move that the model has made, is it good or bad. The rewards can be extremely delayed. It can be that this current move is extremely bad, but 70 moves later, that will turn out to be awesome. So currently, you don't really know is it good or bad. So there are many things here, and the more complex this state space is, meaning the more freedom the model has, the more complicated this reinforcement learning task becomes. That's why You can do chess play, you can do Go, you can do stuff like that.
Yeah, and it's very complicated, because, for example, like when you have a pet dog, I know people do their best to try and reward them to do certain things, but sometimes it can go completely wrong, right? If you do it incorrectly. And similar thing, I remember reading about, Twitter, when they released the source code and all this stuff, and Elon Musk took over. One thing they found was that in social media, like Instagram apparently is very good at selling things to you and recommending the right products. I don't know if you found this, but in Twitter it's terrible apparently. I don't use Twitter myself.
Yeah.
But that was, they said, because they were basically using a reinforcement algorithm, but they were trying to maximize impressions on users. So they wanted users to see as many adverts as possible. But whereas what they should have done is optimize for hang time, where people would be eyeballs staring at products. Because what maximizing impression means is that they will feed you crap, so you scroll to the next advert as fast.
Nice.
So this is a really good example of taking the wrong reward.
They did not fix it, so that's for sure. Twitter ads are garbage. They are the worst ads you can imagine. It is garbage. But that makes perfect sense, because you really have to pick the reward function properly, so you're rewarding the behavior you want to see. No, but in any case, it makes sense. Again, there are many things there, just because every human is also different. You want to have the rewards or the models be different for different people and all of that. So there is a million things that the more freedom you give to a model, the more difficult is it to find the proper reward function. The more difficult is it to train the model, the more data you need to properly train. That's also with Minecraft. When I was doing this, it's like there is a lot of freedom in Minecraft. So Minecraft's a game where you build stuff out of blocks.
If they don't know what Minecraft is, then just leave.
No, don't say that.
Okay, no, don't leave. Stay.
But you have a lot of freedom, because you can do almost everything. You can build houses, you can cut down trees, you can swim in lakes, you can build boats, you can make almost anything you imagine. So it's like a rudimentary replica of the whole world, of options you have in the real world. And with this amount of freedom, then it becomes like unbelievably difficult to find the right reward. Okay, but
anyway, teach me about our RLHF in LLMs, in large language models specifically.
These would be now the 3 types. And we now want to apply this RLHF model to large language models. So we want to apply this reinforcement learning to large language models. What we need is, of course, the best option would be if the reward for the model is coming from the humans. So if every time the model does something, at the end you tell it like, oh, this was good or bad. There are some problems with that. Humans extremely bad at saying how good something is. If you tell me, like, I ask the model a question, like the simplest question ever, what's the capital of France? And the model answers. To me, it is very hard to say on a scale from 0 to 10 how good is the answer.
Perfect one, right?
Yes. Because if the model just says the capital of France is Paris, I can be like, 6 out of 10. Could be better.
I would like that.
It is correct, but I don't know, could be a bit more informative.
You'd like a more complete, like they teach in GCSE English. You need to frame the question. The capital of France is Paris.
So, like, we are bad at basically rating things on a scale from 0 to 10. So how this is done is that the human is at every point shown 2 examples. And those are 2 types of output that are generated either by the same model or by 2 different models. And you are saying which one is better. And we are usually very good at comparing 2 outputs and saying like, oh, I prefer this one. It doesn't even have to be better. It can just be I prefer. What do I prefer?
There's a gut feeling.
Yes, exactly. So we are, with this, we are training the reward function in this reinforcement learning loop. So as we said, in the reinforcement learning, we have the agent. In this case, this is the LLM. and we have the reward function. So we are training the reward function. Now, there are problems here. Turns out, how this works is that I gather a couple of prompts. So I gather a couple of questions that I want to ask the model. So that is a batch of questions. I feed those questions into my model. So this is now, imagine the reward function is trained, everything is ready. I feed those questions into my model and I get responses. For every one of those responses, I rate them using my reward function. So that now the model knows which response is good, which is bad. And then you use a reinforcement learning algorithm to change the parameters of my large language model so that it generates those preferred responses more often.
Makes sense.
Yes, that reinforcement algorithm in this case is called proximal policy optimization. That is the one that it is a very simple model, and it is one of the most widely used today to optimize the parameters of the model.
Now, that's what ChatGPT is built on, essentially.
Yes, exactly, yes. I mean, that's what they say. Again, we are not exactly sure. They don't really make anything really public. But what happens after some time, the model starts to exploit the reward function. The model is much more powerful and tries to basically find loopholes in the reward function.
Yes.
The reward function is not perfect, and over time the model starts to exploit it. And if you just run these in a loop, so basically every time you generate a batch, you have a batch of questions, you get the answer from the model, you update the parameters, then again you find a new batch of questions, and you run these a million times, and then that's how you fine-tune basically the model and align it to human preference. Because this also reward function is called sometimes a preference model, because it is trained on human preference. But after some time, the LLM finds loopholes, and what happens is that the training goes into a wrong direction and starts to basically degrade the model. The model is not getting better anymore, but usually what happens, it starts repeating words. So it will start, instead of outputting a proper answer, sometimes it will just say da 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 da, so it will just say that forever. And for whatever reason, the reward function scores that very high because it's not perfect. So basically it finds loopholes in the reward function.
And that's not the human's fault. So the human preference is correct, but the weights that are changed as a result of that human preference can be exploited. That's what you're saying?
No, the human preference is perfect, but the
is what
reward
changes
model,
after.
The reward model is not perfect.
Yes.
The reward model has problems because it could not learn perfectly human preference.
Exactly. That's my point. So it's
So the reward model has these exploits, and the LLM learns those exploits, and basically all goes wrong. So the model doesn't learn anymore.
And am I right in thinking you could see that in some of the games, or maybe the Atari games, where they find kind of the hacks which humans sometimes have found historically, but the computer knows how to exploit it perfectly?
This would be more in a sense that the model finds a way to do things that you don't want it to do. Not because if you find a hack, that still means you beat the game, probably. But for example, if you tell the model like, oh, you don't want to lose, you want to continue playing, and it finds a hack to just stop and not do anything. Or run in circles, like in Minecraft, run in circles, or do something that is nonsensical, but is still given a very, very small reward, but over time the reward grows because the model is basically, you tell it in Minecraft, don't die, it basically builds a house, goes inside and doesn't do anything.
That's it.
It doesn't die, but it doesn't do anything useful. And the same thing happens here. The model is still generating the output, the reward is awesome, but
it's not what humans want.
It's not what humans want, exactly.
So is that a kind of overfitting in a way?
Yes, that is, the model is overfitting the reward function. and the reward function is not perfect. Yeah, it's fine. It's basically finding exploits. So now you need to prevent these, and this is, like I said, like reinforcement learning has a lot of tricks.
Yeah.
If you just do it, it doesn't work.
So wait, but just like a normal machine learning model, can you not just train less cycles so it doesn't overfit as much?
Yeah, then it's hard to find the right amount of cycles. It's hard to find, and over time, it's even if you have a lot of data and all of that, the model still finds a way to exploit it.
Interesting.
So how you do this is that you employ something called KL divergence. And what you do is, when you start your training, you clone your large language model. So now I have 2 of them. Every prompt, I generate 2 responses. So one is from my clone, the original model, and that clone is frozen. So that clone never changes. I have my LLM here that I'm updating constantly. So there is one model that is updated and there is one that is frozen.
Right.
The KL divergence tells you that the distribution over tokens of the output of the model, of the fine-tuned model and of the original model cannot diverge too much. So you are allowing the model to change the output slightly via the reinforcement learning fine-tuning, but you're not allowing it to overdo it. You still want it to be
not
close.
Be gibberish.
Yeah, you want it to be close to the original output of the LLM.
That's also a tightrope kind of balance, right? Because if your divergence is too small, then the model can't learn from the reward function as well.
Yes.
And you know, and if your base model is flawed and and bad performance, then you're tethering your new model to a crap model.
Exactly that. And that is why your original model has to already be awesome. So when you are starting this alignment to human preference, your model cannot simply be a pre-trained LLM. It has to be a pre-trained LLM that is fine-tuned on millions and millions of instructions. That is fine-tuned via supervised training to basically already know how to answer questions. And then via this fine-tuning, you are not even almost adding new knowledge. You are just telling it how to make the output nicer, safer, more complete. So the model should already have like most of the knowledge inside. 99% of the knowledge is in the model. You are just aligning it. You are just telling it what to do and how to do it so that I like it, basically.
Interesting.
And there are other things here, so I don't want to go too much
I'm thinking of like millions of ways to approach it, but
No, but there are other things here, and this scale divergence is usually added to the reward function as a penalty, so that even if the reward is ultra high, if the divergence is too big, you will penalize the output, you will penalize the reward so that you lower it or you make it even negative. And so after this, of course, you have the proximal policy optimization that comes in play. For that one, you are, again, when you are updating the parameters of the model, for example, you will not update all parameters because models are very big. And updating all the parameters constantly takes a lot of resources. So what is usually employed is you will freeze some layers, you will update only a portion of the parameters. With this, you are also making the model a bit more stable, because if you update all the parameters, you could overdo it and change too many things. So you are making it a bit more stable. There is also quite a bit more regularization that goes into these proximal policy optimization, so that you are again not overdoing these changes and that the changes you make are not too big. And
explain regularization.
Oh yeah, so that just means that I am reducing, or I'm not allowing the PPO algorithm to change the model too much. So when I'm regularizing stuff, I just say like, oh, if it's somewhere too big of a change, I make it a bit smaller. So I don't allow big changes, basically.
I see.
And many of these.
So many tricks.
Yeah, many tricks, and things are very difficult to get right.
Yeah, so there's this concept of perplexity where you can measure in a sentence or a passage how the variability within it and how human-like that text is. So can you use that as also a kind of punishment if it becomes the perplexity is too low or too much? Yeah. If it's stupid, then you penalize it.
No, exactly. You can do a lot of things. So there is a million of these ways to basically do this, and people have tried many different functions how to penalize it more. KL divergence is the one that is winning, and basically that works the best for now. But yeah, there are many ways, and people do also much more, because some things are, for example, you also want to maybe penalize it more if the model is outputting something dangerous. So for that, you usually have other parameters or other scoring and reward functions that are classifying is this dangerous or not, and if it's dangerous, then the reward goes like to minus a million or whatever, so you're making the reward very small. There are many of these, and also when you were mentioning before, like ethical considerations, you also do this here. If you have something that you don't want the model to output because it's not unethical or whatever, then you would add another parameter in the reward function, or even in the PPO part where you're just penalizing the model more and changing it in a way that's more aligned.
Yeah, and this is like a can of worms, because now I'm also thinking you can do adversarial models. So like use other large language models fine-tuned on certain ethics to then rate the outputs of another model.
Oh yes, in fact the reward function is a large language model.
Yeah.
So the reward function in itself in this RLHF is a large language model that is scoring the other large language model.
This is so meta, yeah.
This gets like very messy, and some of the, still, this is the best we have now, next to DPO. So we'll do another one of these on DPO next time, so direct preference optimization.
Yes.
Which is much better. It does not use reinforcement learning, and to me, the moment I have to use reinforcement learning, I think I've done something wrong. So I think if you really have to use it, but I prefer not to use it, and DPO does not use it, and I think it's a better model. And most of the, you were mentioning in the last episode, the leaderboard on Hugging Face. Most of the models today, or a lot of them, don't use RLHF, but really use DPO.
I see.
So there are many benefits if we avoid this reinforcement learning step. But wait, I want to just say, like, this is still very good, because obviously it works, and GPT-4 is made using it, so it is very good. Requires a lot of resources, because instead of one LLM, you now have three. I have my fine-tuned one, I have my original one, and I have the one that is used for rewards. So I'm basically, and imagine if your model is 100 billion parameters.
Yeah, that would be crazy.
That's like, you need 3 times the hardware to run that. It becomes very, very compute expensive. And still, you also need human supervision. So even in this case, you still need human supervision, and you need a lot of these reward training and all of that, which is again expensive because it takes time. And simply this reinforcement learning cycle is much longer than training this model via supervised training. So that is why we are still trying to do most of this training via standard supervised training, fine-tuning the model via supervised training. This is instruction fine-tuning and all of that. And then do a bit of this at the end via RLHF.
I see. So just as a sprinkle on top, but not the core thing.
Yeah, but it does, I don't know, you also see, like, if you play a bit with models and play a bit with those that use RLHF and those that don't, the models that use RLHF become much more fancy. Like, fancy in a sense that if you ask it a question, it will add some words there, like as high schooler who first you learned of like a thesaurus.
Oh yeah.
It will add like words that are like, was it really necessary to describe this in such a like flamboyant way and with all of these?
Yeah, and ChatGPT is a bit like that.
Oh yes, it is very much like that.
Yeah, it's exactly like it's like using fancy thesaurus language as like a university application.
Yes, exactly.
And extra words, like completely verbose. Like you don't need so many words to answer that question.
Yeah, exactly. But that is but it's simply if you show me two examples and one of them is like fancy and nice and the other one is just the answer, a lot of people will prefer the fancy and nice over the Paris.
See, I wouldn't, so maybe
same.
They should have hired us to annotate, to reward the model.
No, same. I prefer like, tell me what it is, don't explain to me.
Tell me what's going on, damn it.
Don't overdo it. But yeah, I think this is all can be solved in the future and we'll see a lot of advancements in this area because again, this is very new. Applying any kind of these alignment techniques to these LLMs is very new, so give it a couple of years.
Yeah. So, I mean, I would love to see, use this kind of approach to train a healthcare model and see what comes out in the end,
Yeah.
But yeah, that's research for another day.
True. Okay, you want to finish up?
Yeah, so we've had a really fascinating episode today. Basically covering the ins and outs of reinforcement learning with human feedback, with some very funny examples, hopefully. And yeah, I think next episode we'll definitely cover DPO in the future. I think that's a very big topic at the moment. But yeah, let's see. Feel free to subscribe and leave a comment. We always love to hear from you and we love it when you reach out. We read every single comment actually, so yeah.
Awesome. Thank you very much for listening and we'll see you next time. Bye-bye.
Bye.